Hello everyone, I'm Jae-min and I'm an assistant professor at College of Computing and Informatics. Today we will talk about pointers in C. So a few days ago, I was asked to make a video that can help undergrads follow the curriculum of our software department. So I have been thinking about the topic since then and finally came up with this topic, pointers in C. I have been teaching the undergrad problem-solving course for 2 years, where we study C programming and use it to solve some programming challenges. And while teaching the course, I found that many students actually have difficulties in using and understanding pointers. Indeed, pointers are one of the most hard to understand concepts in C, I think. And I think it can be the first hurdle that you will encounter when you study C by yourself. So this is why I decided to record this video. I will talk about why pointers are needed and how to use them and what are the caveats that you should be aware of when you use pointers. This video mainly aims at students who have heard of pointers but are not confident in using them. But even though you are already familiar with pointers, I think it can be a good opportunity for you to review the concept. If you are totally unaware of C programming, then unfortunately this video is not for you. Okay, so let's get started. To understand pointers, you need to understand the memory first. So what is the memory of a computer? This is the physical device. So this is RAM, random access memory. And you can see that it consists of some multiple black chips. And they are actually storing some information. But even though physically the memory consists of multiple chips, it can be seen as a single array of bytes logically. So this is kind of abstraction. We are not interested in how the actual memory is implemented, but we are just interested in how to use it. So memory can be seen as an array of bytes, very long array. And each byte in memory is assigned an address starting from 0. So this array consists of cells, with each cell storing 1 byte. So 1 byte. And it is assigned an address starting from 0. So 0, 1, 2, 3, 4, and so on. And theoretically, a 64-bit computer can handle 2 to the power of 64 different addresses. So when we talk about operating systems or CPU, we use this expression, right? 64-bit or 32-bit or 16-bit, which is kind of old. Anyway, 64-bit computer means that it can handle this amount of different addresses. And 2 to the power of 64, this is a very big number. So this is huge, and your desktop may have less than 64 gigabytes of memory, which is 2 to the power of 36 bytes. And this number is very small. Is much smaller than this number. So we are only using a very small fraction of the theoretically possible memory addresses. So here is a logical view of memory. We have very long array, and each cell has its memory address starting from 0. And one cell in this array can store 1 byte of information. And you may know that 1 byte consists of 8 bits, and 1 bit can represent either 1 or 0, so binary state. So if you zoom in to this cell, then you will see 8 bits, which is 1 byte, and each bit can have one of the two states, 0 or 1. here I put some numbers. So this byte has a bit sequence of 01000001, which corresponds to 65 in decimal. So each byte, so each cell in the memory can store a number ranging from 0 to 2 to the power of 255. And one thing you should remember here is that a memory address is assigned to a memory cell or a byte. For example, 0 is the memory address of the first cell or first byte, and 1 is the memory address of the second cell or byte. And there's no memory address for each bit. So if you want to access or read a specific bit, you should first access the byte or the cell that contains the bit and do some bit manipulation to read this value. So when you talk about pointers, you don't have to think about these bit representation because they are not accessible. So from now on, we will not consider this bit. So the byte is the smallest amount of space that a pointer can point to, like the cell. And here I defined two variables, character A. So character is the type of a variable, and A is the name of the variable, and in B. And you may know that in C, different types have different sizes. So for example, a character type takes up 1 byte of memory space. So here we have capital A, whose ASCII representation is here, so 65 in decimal. And for B, B is an integer type, and an integer type in C takes up 4 bytes of memory, 4 consecutive memory address. So here, B uses the memory space starting from the address 4 to address 7, right? So these 4 bytes is used for B. So here's the thing. To understand how pointers work, you need to remember these two principles. Actually, they are not principles, but I just named them principles because they are so important. The first principle is that there are two numbers associated with a single variable, its value and its memory address. They are equally important, but many students just think about the value, not its memory address. And this is, I think, the first reason why they have difficulties in understanding pointers. Here's an example. So if you define and use a single variable like this, you are actually working with two numbers. So one is its value, and the other is its memory address. The value can be accessed by an expression like this, just A. It evaluates to the value stored in this variable or this memory space. And while the other memory address can be accessed by an expression like reference A. They are equally important. But the name A is convenient, right? Because it hides its memory address. But actually, this name is translated to the low memory address, which is done by a compiler. So compiler is a special program that does this job. And one reason why I think students have difficulties in about pointers is that most C operators are about the value, are interested in and manipulating these values. For example, we have plus, minus, multiplication, division, and so on, some comparison operators as well. These are mostly used for values of a variable, but they can be applied to point memory addresses as well. And the second principle is that every memory space has its address, but some memory space does not have a name. So address is universal because every cell in the memory has address. Every byte in memory has its address. But name is not universal. Some memory space, some bytes in memory have a name. For example, memory space allocated by dynamic memory allocation, malloc, does not have a name. So you cannot use a name like this A. So, but there should be a way to refer to this memory space that does not have a name. In that case, we need to use the memory address directly because it's universal, and to do this, we use pointers. So pointers are a more universal way to access the memory space. Let's go through some examples. So here we have a statement, x assign 3. So what is the meaning of this statement? You may interpret this like this. So assign 3 to x. But more concretely, this means that assign 3 to the memory space that is named x. So x is a variable, but this is a logical concept. It actually refers to a specific memory space that is named x. So x is the memory space that is named x, and this is the most concrete interpretation. So this is what happens. We have a variable x, integer x, and it takes up 4 bytes of memory, and is located at memory address 4. And because you assign 3 to it, so 3 is stored in this memory space. So this is what happens if you execute this statement. And here's another example. So x assign y. We have 2 variables. So this statement can be interpreted as assign y to x. It's correct, but this is the most higher level interpretation. And let's break it down. So this means that assign the value stored in y, because a variable name on the right hand side of assign operator is evaluated as its value. So assign the value stored in y. This is what y actually means, and to x. And we can also interpret x more concretely like this. So assign the value stored in the memory space named y, right? They are equivalent. And to the memory space named x. So this is the interpretation of x part. So we have 4 in y, and we access the value stored in the memory space named y. So we read this 4 and we assign it to memory space named x. So this becomes 4. So basically this is a copy operation. So far it's easy to understand, right? In both statements, we specify the memory space using its name, x and y. But as I told you before, not all memory space has its name. So in that case, we need to use memory address directly. To this end, we need to have a special operator that allows us to access a specific memory address, which can be done by the reference operator, dereference. So in the previous slide, we used the reference operator. This is reference operator, ampersand, and star. This is dereference operator. The dereference operator star allows you to access a specific memory address. As I told you before, this is more universal way to access a memory space. So here's an example. Star, draw x, 1, 2, 3, 4, 5. So assign 3. So 3 is the number. So this is just constant. So we are not interested in the constant. And we have the memory address. So draw x means that the following number is in hexadecimal, but it's not important because you can provide the memory address in decimal. So this part is not important. And 1, 2, 3, 4, 5 is the memory address that you want to access and store this number. And this star means that we will access a memory space whose address is this number. So this is kind of access. It means access. So this statement can be interpreted like assign 3 to the memory space whose address is draw x 1, 2, 3, 4, 5. In the previous slide, this part was like named x, right? But we are use more direct way, and even though you use a name, like a variable name here, in this part, eventually it is translated to the memory address like this, which is done by the compiler. So this is just a convenient way to name a specific memory space. But if you run this code on your computer, it will not run because the address drax 1, 2, 3, 4, 5 is unlikely to be allocated for your program. So this expression by itself does not have any problem. So it's, in terms of syntax and in terms of semantics, it's totally fine. But the problem is that your operating system does not allow your program to access an arbitrary memory space, an arbitrary space on the memory due to some security reasons. Because one program can, if one program can access any memory space, then it will break the other programs to run. Or you can put some malicious code in the memory, to the memory. So this code doesn't work, but in terms of syntax and in terms of semantic, it's okay. To make the previous example run, we need to use a memory address that is actually accessible. And one simplest way to do this is define a variable. So if you define a variable, the operating system allocates some memory space that corresponds to the size of the type of the variable, and this memory space is totally accessible. So get the memory address of an existing variable, then the problem reduces to how to get the memory address of a variable. We already talked about this question, right? We had the reference operator. So the reference operator ampersand allows you to get the memory address of a variable, and it doesn't make sense to apply this operator to constants. For example, reference 3, it doesn't make sense because 3 is a constant and it doesn't refer to memory space. This is just a number. But reference A, this makes sense because A is a variable, so there should be memory space associated with this name, and we are getting the address of the memory space. And one characteristic of this reference operator is that the address of a variable will change from run to run, but never change in a single run. For example, if a variable A is, the name A refers to memory space drax 1, 2, 3, 4, 5, then the association between these two things is fixed throughout the execution of your program. If you run the same program again, maybe the name can be allocated to different memory space like 2, 3, 4, 5, 6, but still in a single run, this association doesn't change. So here is the example. So I changed the previous example and make it run. So int y assign 4 and x assign reference y and the reference x assign 3. So let's take a look at this example in more detail. The first part of the example is int y assign 4. So this is simple. So you allocate a 4-byte variable y and initialize it to 4. So here I will assume that the pointer, the x, is already defined. So in memory, we have two variables defined, int star x. So this star means that x is a pointer variable, but for now, just ignore this symbol. So x is a pointer variable, and each pointer variable takes up 4 bytes of memory on 64-byte machine. We will talk about this later, so forget about it for now. Anyway, this memory space is allocated for the name x, and this 4 bytes of memory address, partially hidden by my face, but this part is allocated for the name y. And we initialize y to 4, so it stores a number 4. And the second statement was x assign reference y. Here, the reference operator comes into play. Here, this expression means that we get the address of y. So what is the address of y? So let's take a look at the picture. We have y, and 4 is the value of y. And I told you that there are two numbers associated with the variable. So one is value, and the other is memory address. The memory address of y is not 4, but 8. So actually, y spans 4 bytes in memory because its type is an integer. When we talk about the memory address of a variable, we use the starting memory address, so which is 8. So if you reference y, if you use this expression, reference y, then this evaluates to 8, not 4. And this is what the reference operator does. And you get the memory address of y, and you assigned it to x. This is a simple copy operation. And 8 is stored in the memory space named x. So 8 to here. So let's take a look at the last part of the example, the reference x assign 3. This is the most challenging part, actually. So we have 3 and we have assignment operator. There's no problem, but the problem is the reference x. So what it does is that first we read the value stored in x, which is the memory address of y, and the reference operator accesses the memory space whose address is the following number. So here the following number is the value stored in x. So the statement can be interpreted like you assign 3 to the memory space that x points to. This is a high-level interpretation. And let's break it down. So you assign 3 to the memory space whose address is the value stored in x. So they are the same. And the value stored in x is actually the address of y. Right? In the previous statement, we assigned the memory address of y as the value of x. So this is equivalent to you assign 3 to the memory space whose address is the address of y. Then this part reduces to just variable y. So here you are actually assigning 3 to x, but in this statement there is no y, right? We accessed y via a pointer variable x. So even though we didn't use the name y, you can access it by its memory address. So the name is just optional. Name is not necessary. So in this example, the reference x works as a proxy to y. Actually, they are equivalent. So you can see the reference x as an alias of y. They are just the same. If you can do some operation on y, you can do the same operation on the reference x as well. So you can replace y in an expression with the reference x without changing the behavior. But you should remember that x is different from y. X and y are just different variables. They refer to different memory space, but the reference x is equivalent to y. And here is another example, so take a look. In the first code, we have z, which is another integer variable. In the second part, we have x, which is a pointer variable, and z stores the value in y, while x stores the memory address of y. So z assign y, because y is 4, z is initialized to 4, and we overwrite this 4 with 3. So z becomes 3. So you can see that z and y are just different variables. There is no relationship. So if you modify z, it doesn't affect the value stored in y. No relation to y. But in the second example, x assign reference y. So x stores the memory address of y like this, 8. And the reference x assign 3. The reference x means that we access the memory space whose memory address is the value stored in x, which is y. So 4, initially y was 4, but it changes to 3. So y is updated via x. So there is some relation. But you should be aware that if you just assign a number to x itself, it doesn't affect y. So it can affect y only when you use the reference operator. Alright, so far we have covered some fundamentals about pointers, and here are more kind of advanced topics about pointers. So let's go through these topics in the rest of this video. First, we're gonna talk about how to define a pointer variable. To define a pointer variable, you can use the operator star or reference. So there are name conflicts. For example, star usually means multiplication, right? But star as a unary operator, it means reference. Like, for example, A star B. Here, star means multiplication, right? The product of A and B. But star B here, this means reference B. And if you multiply A and the number that B points to, then A star B. So this is correct interpretation. But if you use star in the definition statement, it means that the following name is a pointer variable. For example, int star p. It doesn't mean that access the memory space pointed by p, but it means that p is a pointer variable because it's in the definition statement. So it's kind of confusing, right? Because the same symbol is used for different purposes. Int star p, p is a pointer variable and assign reference num. So num is another variable which is defined the first statement, and we get the memory address of num. And if you print out p and the reference num, you can see that they are actually the same because you just copy the memory address to p. And p here, this is a special format specifier which is used for printing out a pointer address. By default, the number is printed like in hexadecimal. So it means 0x009ff9c8. Sometimes you define more than one variables in the same statement, and one of them is a pointer variable like this. So int star c comma d. So we are defining two variables, c and d. But because star is here, star follows the integer type. So this statement can give an illusion that both variables are pointer variables. So both variables are of type int star, but actually they are not. So c is a pointer variable to int, but d is just an integer variable. So this happens when you use a text editor that supports auto indent or auto formatting. So auto indent in Microsoft Visual Studio automatically moves the star right after the type name, which can give an illusion that both variables after the type are pointers. But the first one, so just right after the star symbol, is interpreted as a pointer variable. Others are just type of int. And to print out a pointer, actually printing out a pointer means that printing out the memory address stored in a pointer variable. So this is a more correct interpretation. So use %p format specifier. So as I told you before, so %p pointer, actually this is a memory address. So we get this value. And on computers, addresses are just numbers. So you cannot distinguish memory space from value. So it's up to you. So it's up to interpretation. Addresses are just non-negative numbers. So you can use %d as well. For example, here I used %llu because the number was very big. So this is a long unsigned. So this is a format specifier that you use to print out a unsigned, so positive, non-negative, long integers. So if you print out this number in LLE, you can get this big number. In this example, you need to focus on the output. So in the last example, we got 8 hexadecimal digits as a memory address, but is it correct? So does it represent a 64-byte memory address? Because here we have 8 digits, and one hexadecimal number or digits can represent 16 different values from 0 to 15, which is 2 to the power of 4. So 8 digits can only represent 2 to the power of 32. So 2 to the power of 4, this is the number that one digit can represent. And there are 8, so 2 to the power of 4 to the power of 8, which is 2 to the power of 32. It can only represent 2 to the power of 32 different values, but this is much smaller, right? Because on your 64-bit computers, we need to have represent a memory address up to 2 to the power of 64. Actually, this only this amount of memory address can only represent 4 gigabytes of memory. This is quite small in these days. So why this happened? This is because your machine is 64-bit, but you compile the program as a 32-bit program. For compatibility, many compilers by default compiles a program into compiles your source code into a 32-bit programs, because 32-bit programs can run everywhere, but 64-bit programs can be run on 64-bit machines. So you need to change the target platform to a 64-bit platform, and you will get 6 hexadecimal digits as a memory address as expected. So in Microsoft Visual Studio, if you take a look at the toolbar of your interface, then you can see that here by default the compiler, the option is set to x86, which means a 32-bit program, and if you change it to x64, then and run your program, then you will get this result. And you can see that 16 hexadecimal digits are printed out, which can represent to the power of 4 to the power of 16, which is to the power of 64 different memory addresses. So we have talked about how to define and print out a pointer. Here we talk about the type of pointer. So memory addresses are just 64-bit data. So it can be stored in any 64-bit type, like double or long. But for pointers to explicitly specify that the number is a memory address, we use special types, which we call pointer types. So this is for strictness and convenience. If you just want to store memory addresses as data, then you can just use integer types, so long integer types. But this is ambiguous, right? It's hard to distinguish values and addresses. But if you use pointer types, then we can assume that numbers in pointer variables are memory addresses and others are just numbers. And when you define a pointer type, you need to specify the type of the variable that a pointer points to. So star before a variable name means that a is a pointer variable, but additionally we need to specify the type of the variable that a points to, like integer. So this part tells the machine how many bytes must be read from the given address when dereferenced. And this is very important information that must be given to the compiler to compile your program, your code successfully. So here's an example. So we have a variable y whose type is integer. So it takes 4 bytes, and these 4 bytes together represent an integer 3. And x points to y, and you execute dereference operation. So dereference x. So because the memory address stored in x is 8, we access the memory address 8. But the problem is that how many bytes we have to read from the memory address 8. It depends on the type of the variable that is pointed by x. Without this information, we cannot retrieve the value stored in the variable that x points to. For example, if x points to a 1 byte variable, then the value should be draw, right? Draw is stored in the memory address 8. But if it points to a 4 byte variable, like in this example, y, then we should read 4 bytes together. And the result will be different. So in the second case, the result will be 3, not draw. So the pointer variables should provide, so we need to provide how many bytes should be read when the pointer variable is dereferenced. And this is why we put this part before the pointer type. So without a type, like int star, the compiler does not know how many bytes should be read at 8 when referencing a pointer. So this integer keyword is necessary. So in summary, int star means the type of a pointer to an integer variable, and the double star is the type of a pointer to a double variable, and in an abstract way, x star is the type of pointer to a variable of type x. X can be double character or long or integer float or structure types. And regardless of the type of the variable a pointer points to, the size of the pointer itself is always 8 bytes because it holds an 8-byte memory address. So int star, the size of the variable that an int star pointer points to is 4 bytes, right? But the pointer variable itself takes up 8 bytes regardless of the type of the variable that it points to. So size of int star is 8, size of double is 8, size of double star is also 8. So int and double have different sizes, 4 and 8, but int star and double star have the same size, which is 8 on your 64-bit machines. If you use a 32-bit machine, then this number will be 4, not 8. And here comes a more complicated thing, a pointer to pointer. So a pointer is also a variable. There is nothing special. It can just store the memory address, which is 8 bytes of data. So we can define a pointer variable that points to another pointer. So a pointer to pointer. Yeah, things get difficult. Type int star is the type of a pointer to an integer variable. But if you put another star, type int star star is the type of a pointer to an integer variable. So double nested pointers. Size of int is 4, size of int star is 8, and size of int star star, this is just a pointer variable, so also 8. Okay, this is an example about a pointer to pointer. So here we have a variable a, int a assign 1. Right? A takes up 4 bytes and it stores 1. So if you evaluate this expression a, you will get 1. So no problem, right? Here in the second statement, we assign the address of a. So what is the address of a? 16 is address of a. 1 is the value of a, not address. So we assign 16 to a pointer variable b. And b is a pointer variable, so it takes up 8 bytes in the memory. So this long, 8 bytes. And it stores 16. And if we evaluate an expression b, then you will get 16, which is the value stored in the variable b. And here we have a pointer to pointer. So reference b. What is the address of b? B is here. And its address is 20. So we store 20 in C. So C has 20. And it takes 8 bytes of memory because it's a pointer variable still. So if we evaluate C, we will get 20. Alright, so we are done with this part. And let's put the reference operator in front of each expression. So the reference A, it's the memory address of A, which is now stored in B, right? So memory address of A is 16. So we'll get 16. Memory address of B is 20. And memory address of C is 28. You can see that these two values are the same and these two values are the same, right? Because we assigned these values in B and C. What about dereference operator? So dereference A, it doesn't make sense because A is a variable, just a plain variable, so you cannot put dereference before it. The compiler doesn't allow this operation, so it's an error. Dereference B, it makes sense because B is a pointer variable, so B it holds the memory address of A. So this expression evaluates to the value of A, which is 1. You can see these two numbers are the same. Dereference C, this means C holds 20, and we go to the memory address 20 and read the value, which is 16. So 16. So you can see these values are the same. Dereference A. Dereference A doesn't make sense. So dereference A doesn't make sense as well. Dereference B. In this time, dereference B is a memory just a number 1. So you cannot access the memory address 1. It doesn't exist in this scenario. And dereference C here, dereference C means the pointer. Dereference C is B, and B is the memory address of A. So dereference B means A. So it reads the value of A, which is 1. So they are the same. So you can see here these three numbers are the same, and these three numbers are the same, these three numbers are the same. So this is just an example to understand how a pointer to pointer works, and you should spend some time to understand these tables, and you need to be able to draw a picture like this when these three statements are given. So think about how many bytes each variable spans and the value stored in each variable. And in the previous slide, I told you that when you define a pointer, you need to provide the type of a variable that the pointer points to. But actually, it's not mandatory. So we have a special pointer type, which is void pointer, that allows you to omit that part. So a void pointer or void star is a pointer that has no associated data type with it. It can hold address of any type. It can hold the address of character variables or float variables or int variables, but it must be typecasted before dereferenced. So here's an example. Int A 3, assign 3, no problem. Void star B, so B is a pointer to a void type, assign reference A. So B is holding the memory address of A. There's no problem because regardless of type, the size of the pointer type is 8 byte. So B is just holding 8 bytes of data. But the problem occurs when you dereference B without typecasting. So dereference B, it doesn't make sense because the compiler does not know how many bytes should be read from the memory address that B points to, because we didn't provide the type. So B can hold the memory address, but it does not have information about the length of the original variable. So before we dereference B, you need to convert a void pointer to an integer pointer like this. This is just a typecast, and dereference it. This is correct, and the compiler knows that it should read 4 bytes from the memory address stored in B. You need to determine this before you dereference a void pointer. and you deliberately typecast a void pointer to a different type to just see what happens for fun. So here's an example. We have A is a character variable, B is an integer variable, and C is a double variable. So these three variables have different sizes, but they all can be pointed by a void pointer, because a void pointer can point to any type. So void star P assign reference A. So P is pointing to A, which is a character variable. If you so to access the value stored in A, you need to typecast P to character pointer first, then the reference. This evaluates to 1. And P is now pointing to C, which is a double variable. If you print out the value stored in P correctly, you need to typecast P to a double pointer variable, right? Like double pointer P and dereference it. Then you will get the number, the pi value. But if you deliberately typecast the pointer variable to a different type with different size, like int star, here, double star and int star takes up 8 bytes, but P here is pointing to an integer variable which has different size from a double variable. Then only first 4 bytes of the original variable is read, so the number is broken. It's this number. Yeah. So, so to understand why this specific number is printed out, you need to know how the floating point numbers are represented in C. But never mind. So the important thing is that you need to, when you typecast a void pointer, you need to typecast it to a proper type. All right, that's it for pointers. And I'd like to conclude this video with showing some practical examples. So when you study C, you will see pointers in array parameters like this. Void f, so f is a function, and it takes a pointer parameter. So I summarize the 3 most common reasons for this pattern. So why do we use pointer parameters? This is just my personal classification, but I think it covers like 90% of use cases, but there can be another reasons. The first reason is to modify variables outside the function. The second reason is to pass big data structures without copying. And the third reason is to pass a multidimensional array with its structure kept. So let's go through each reason. The first reason that we use pointer arguments in the function definition is to modify external variables. So sometimes we need to modify a variable that is defined outside of the function. One practical use case is to return more than one value as a result of the function. So this is not possible, not allowed in C by default. So in Python, you can return more than one variable or more than one value as a tuple. But in C, a function can return either 0 values or 1 value. So no 2 values. So to implement this, we store the results in the variables that are given as parameters. We will talk about this example later. But anyway, we need a way to modify a variable outside the function. So here's an example. We have a function set4, which takes one integer variable a and assign 4 to it. So a assign 4, right? And in the main function, we define another integer variable b and initialize it to 5, like this, b assign 5. And we call set4 with b as a parameter. Actually, b is an argument here. this is an argument for a function call. So our expectation is that after calling set4 on B, the value stored in B changes to 4. Because if you take a look at the definition of set4, set4 takes one parameter and changes the value to 4. And we pass B as an argument, so the value, we expect that the value of B is changed to 4 after the function call. But in fact, it doesn't change. So if you print out B after the function call, you will get 5, which is the initial value stored in B. So set4 does nothing, in fact. So why? Because in C, by default, function call is done in a call by value way. So variables in the argument list of a function call, so variable here, B, mean their values, not their memory address or not their memory allocations. So here B has two numbers, address and value. And if you call a function on B, its value is just copied to the variable in the parameter list. So 5 is just copied to A. And A and B are totally different variables. There is no link between them. So even though you change the value of A in the function in any way, the value of B outside the function does not change. So this is kind of safe option, right? Because the function is isolated. But the problem is that in some cases, we need to change the function variables outside the function, breaking this isolation. To do this in C, you can use pointer variables. So here's an example. Set4 takes A. A is not a plain integer variable, but a integer pointer variable. So it holds the memory address of an integer variable. And we assign 4 after dereferencing A. So we store 4 in the variable in the memory space that is pointed by A. And when you call set4 in the main function, you need to provide a memory address. So by using the reference operator, you provide the memory address of B as an argument. So here is the figure that illustrates what happens. So suppose B is here. B is an integer variable and initialized to 5. And its memory address, which is 24, is passed as an argument. And it's stored in A, 24. In the body of the set4 function, because the function dereferences the memory address first, and stores 4. So 4 is stored in the memory space whose address is 24. And from the main function's point of view, the memory address 24 is where the B resides. So eventually, it seems that so B is updated after calling the set4 function. So 5 will change to 4. So we pass reference B instead of B. In set4, we cannot access B directly due to the scope rule. So you cannot access the variables outside the function directly. But we know the address of B, which is stored in A. So if we change the value stored in that address using the referencing operator, then B will change. So in this way, you can make a function change a variable outside the function itself. But still, it's called by value function call. So I saw someone say this pattern uses the call by reference function calls, but it's wrong. There is no call by reference in C. You cannot implement that. To call by reference function calls, you need to use different languages like C++. In C++, it's possible. Because in C, in this case, although we pass the address of V, the address was still copied. So it's not called by reference. So still called by value. So one example is that, for example, here, int C, star C, reference B, and this part C. So this is this version of code is equivalent to the original code, but in this case, we can change the value of B in the function via A, but still we cannot change the value stored in C. Right? If you implement call by reference in the function, you should be able to change the value stored in C itself, but in C it's impossible. Okay, so everything is called by value in C. So coming back to the motivating example, let me talk about how to return more than one variable as a digital type of function call. So in C, returning two values are impossible, but what we expect will look like this. So return 10 and 20. So this init function returns two values at the same time, which is impossible for now. Because this is impossible, we need to change it to the definition with pointers. So in this code, we return 10 and 20 and assign each number to different variable x and y. So x and y should be, the value of x and y should be changed after executing this statement. So to make this pattern possible, you can pass x and y as pointer variables. So init reference x and reference y, and in the init function you get the address of the variables and change the value by dereferencing them, like star x, dereference x, dereference y, 10 and 20 respectively. So the result is the same. So the value of x and y are both changed to a different number. But this is just a workaround, and in C there's no way to return more than one variable or one value. And the second reason that we use pointers in function parameters is to pass big data structures without copying. So here's an example. We define a structure type map_t, which has two member variables, actually arrays. So the first member is keys, an array of 1 million integers, and the other is values, which is also an array of 1 billion integers. So you can see that this type is very big. So in fact, because an integer takes 4 bytes, we need 4 times 1 billion megabytes of memory to store the first array, and another 4 megabytes of memory is needed to store the second array. So in total, we need 8 megabytes of memory to store one variable of this type. And here we have a function that takes map_t type as a parameter. The problem is that when you call this function like lookup map blah blah blah, then this function, this argument is copied to this variable. So this is what we said in the previous slide. So we called this call by value, right? So each time you call this function, you need to copy 8 megabytes of data. This doesn't take too long because modern computers are very fast in copying data from memory to another location. But if the if we call this function many times, very frequently, then it can be an overhead. But if you take a look at the body of the function, the map variable doesn't change. So we only read some values from it without changing it. So for this purpose, you don't need to copy the entire data structure to the function code. But by just passing the pointer to this variable, you can reduce the overhead for copying. Here is an alternative. So you can see that instead of normal variable map, we use a pointer. So map is a pointer to a map underscore t variable. So if you call the lookup function like reference map, blah, 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 then only 8 byte, which is the memory address of this variable, is copied. So this is much faster than the example in the previous slide. And another change that you should make is, because map is a pointer to a structure, you need to use this arrow operator. So it was the dot operator, which accesses the one member of a structure, but if map is a pointer, then you need to use this arrow, right? But the semantic is actually different, because here map is a pointer to a variable of type this type. So because this has the memory address, you can change the actual map variable through this pointer. So map can be accidentally modified by programmer's mistake. So in this code, there's no problem, but the programmer can make some mistakes by accidentally changing the variable that this pointer points to. To be safe, you can add the const keyword in front of the pointer definition, like const map underscore t star map. So map is a pointer to a variable of this type, which is const. So as its name suggests, it makes the original data read only. So you can read the data. So you can read these keys and values, but you cannot modify the element of this array. So it can be safer. So const something star the variable name. So this pattern is quite common. And the last reason that we use pointers in function parameters is to pass an array as an argument of a function call. For example, here we have an array, ARR, that has 5 numbers, and you want to pass this array as an argument like this. So this is totally possible. But to take this argument, you need to define the first parameter as a pointer, because in C, an array name evaluates to the memory address of the first element of the array. So to take that memory address, you need to define a pointer variable. So here, like this. So ARR is a pointer to an integer. Actually, it points to the first element of the array where 1 is stored. And using this pointer, you can access the element of array like this, array sub I. This is the same as how we access array element using the array name. But the difference is that ARR just points to the first element, and we do not know how many elements are in the array. So you need to use an extra parameter, which is n. So n represents the length of the array. So you can iterate the I loop from 0 to n to sum up the numbers in the array like this. Without n, you cannot find the length of the array. Like a one-dimensional array, you can pass a two-dimensional array to a function like this. Array sub3 sub3. So this is 3 by 3 two-dimensional array. And fill array comma 3. So array here. So you can, if you see the type of P, so P refers to, the P points to a two-dimensional array, and the type is a little bit complicated. So let me interpret it. So P is a pointer. So int star P. Sorry. Int parenthesis star P sub 3. So P is a pointer to an array whose rank is 3, and the array consists of integers. So P is a pointer to an array of 3 integers. And this 3 is the number of columns in the two-dimensional array. The number of rows is unknown, so we need to pass it as the second argument of the function call. So this 3 means the number of rows, and here, and this 3 means the number of columns. And you can use these nested for loops to access each element in this matrix. And you can extend the previous code to 3, 4, or n-dimensional arrays. The key is to specify all the dimensions except the first, like this. So array is 4-dimensional arrays, and if you want to have a pointer to this array, this 4-dimensional array, you need to specify all the dimensions except the first. So P is a pointer. P is a pointer to an array consisting of 4 items, each of which consisting of 5 items, each of which consists of 6 items, each of which is an integer. So you can you can store the memory address of ARR in this pointer, and you can access the original multidimensional array via this pointer like this. Alright, so so far we have covered the 3 most common cases where we use pointers in function arguments. That's it for my lecture, and I hope this video helps you understand the concept of pointers in C and how they work. Alright, thank you for your attention. Bye.